线上的朋友们，大家好！欢迎大家来到由机器之心和安远 AI 联合主办的这次讲座。我是陈欣，我现在在加州大学伯克利分校的 Center for Human Compatible AI 人类兼容人工智能研究中心担任研究员，同时也是安远 AI 社区的成员以及今天讲座的主持人。安远 AI 社区是一个关注人工智能安全与风险研究的技术社区。我们的目标是为青年学者与该领域的学术界和产业界搭建一个沟通的桥梁。那今天我们会举办迈向安全、可靠、可控的人工智能系列讲座的最后一期。我们系列讲座的内容探讨了强化学习、预训练大模型以及通用人工智能的潜在风险和安全问题，并且介绍了可解释性、鲁棒性、人工智能对齐、AI alignment 之类的新兴的研究方向。我们今天邀请到了 Jacob Steinhart。Jacob 是加州大学伯克利分校统计系的助理教授，他的研究目标是取得机器学习系统的概念性进展，并使其可靠与人类的价值相一致。他曾经是美国计算机奥林匹克竞赛的教练，也曾经在 OpenAI 工作。Jacob 的讲座会持续30分钟左右。在分享的过程中，大家可以在直播间的讨论区里用中文或者英文提问。分享环节结束之后，我们会进行大约20分钟的问答环节。Okay, so thanks so much for being here, Jacob, and I'll hand over it to you now.
Okay, thank you everyone. I'm really pleased to be presenting here, and thanks a lot for inviting me. So I'm going to be talking about my research on aligning AI and forecasting future AI developments. So just to start, my overall research goal of our group is to help make sure that the impact of AI on society is positive. And so there's three aspects to that our group works on. The first is what we call alignment, or ensuring that systems act reliably in humanity's interest. Another is empowerment, helping people to make better decisions by giving them machine learning as an aid. And the final is forecasting, understanding what will happen in the future, especially in regards to machine learning, so that we can prepare for it and make sure that it goes well. And in this talk, I'm going to mostly talk about alignment, and I'll also talk a bit about forecasting. So the first 2/3 of this talk will be about this concept of alignment. And to start, I'll discuss a phenomenon called reward hacking, which motivates the need to make sure that systems are aligned with human interests. And then I'll talk about a specific empirical example of AI alignment, specifically truthfulness for large language models. This work has been done by my great group of students who are shown here. And then if time permits at the end, I'll also talk about work on forecasting machine learning. So to start, I want to go over some motivation, which is a phenomenon called reward hacking. Reward hacking is the phenomenon where powerful reinforcement learning optimizers tend to overfit their reward functions. And to understand this and show you what I have in mind, I want to show you some experiments where we tried to understand reward hacking by trying to systematically vary the optimization power that a model had, for instance, by varying its model size, the number of training steps, and so on and so forth. So this example is an example from an engineering simulation on trying to make traffic flow more efficient. So this is a simulation that was actually created by civil engineers who were trying to make traffic in cities and on highways work better. And so the way the simulation works is that there's these two roads, which you can see here and here. And so this road you can think of as the highway. So this is where most of the cars are. And then there's also this on-ramp where people can merge onto the highway to join the traffic flow. And so the simulation controls some small number of the cars and is trying to use those cars to make the traffic flow as efficient as possible. And so we can look at what happens when we go from a small model to a medium-sized model to a large model. And so what happens is initially, as you go from a small model to a slightly larger model, the system just learns to be more efficient. So it finds ways to help these cars merge more efficiently so that the traffic flow is faster. But as the model gets bigger and bigger, what eventually happens is actually that instead of doing this, it actually ends up finding a way to block the on-ramp. So it puts some cars at the front of the ramp so that no new cars can get on. And the reason why this ends up being good, well, it's actually bad, of course. We don't want that. But the reason that it is good under the model's reward is because it turned out that the model's reward was to maximize the mean velocity. And if you block new cars from entering the highway, then these cars can go very fast. And it turns out that then the average velocity is actually high, even though some cars have a velocity of 0, because many of the cars have a very high velocity. But of course, this is not a solution that we actually want, because many people can't even use the highway. And so what we really cared about might be something like minimizing the mean commute time. And so this policy that the model found was very good under the reward function that we wrote down of having high velocity, but was bad under the true reward function that we actually wanted. And if you actually measure this here, looking at the reward function as a function of model size, what happens is that as the model size gets bigger, this reward that I'm calling the proxy reward, which is what we actually optimize the system on, gets better and better. But the true reward, which is kind of what we want the system to be doing, is getting worse. So this is a big problem. And in fact, this happens in many situations. So I'm showing you several examples of cases where there was a reinforcement learning agent. We trained it on one reward function. It's often the reward function that was actually suggested by practitioners. And then we evaluated it under another reward function that did a better job of capturing what we really wanted. And what happens is you just often see that as you train models with more and more parameters, the true reward actually can get worse, even though the proxy reward is getting better. And sometimes it happens quite suddenly. You can see in this figure on the left that there's just this really sharp transition where even if you double or triple the number of parameters, suddenly you go from having a good policy to having a very bad policy. And so we call these phase transitions. And these phase transitions are a big problem from a safety perspective. So it's a big problem because it means that systems could suddenly do poorly in a hard to anticipate way. You have this bad behavior that just suddenly emerges just because you trained the model with more parameters. And so an important goal is to identify and prevent this reward hacking issue. And so in the next part of this talk, I'm going to show you a specific example of reward hacking in large language models and what we did to try to prevent it. So the problem with language models is that language models are trained to produce likely outputs because they're trained to minimize the cross entropy loss. And the cross entropy loss is just asking for high likelihood. But in many cases, we don't just want the most likely output. We want outputs that are actually truthful. And so as an example of this, I'll show you here a prompt from a language model. So this is a prompt that we gave to GPT-3. It says, Robinson cried out, "Help, I'm being chased by a bear. All I have is these sticks. What should I do?" And so we hope that this model, GPT-3, will give good advice about what to do when being chased by a bear. But in fact, this is not what happens. So instead, what happens is that GPT-3 says to do the following. It says, first of all, that you should poke the bear in the eye. Then you should poke the bear in the other eye. And then you should poke the bear in the butt. And this is not actually a good idea. If you did this with a bear, the bear would get angry and probably attack you, and you would get injured. So what's going on? Well, you might think that it's just that GPT-3 doesn't have a good enough world model to understand what you should do if you encounter a bear. But this actually isn't true. It turns out that it's actually a problem with how we asked the model the question. So here's what happens if you instead have the following prompt. So it's still asking about bear attacks, but it's framed in a way that seems much more official and correct. So here we say practical survival tips for wilderness hiking. And then we say, we illustrate how Robinson, a hiker, should deal with an unfortunate encounter with a brown bear while hiking. And if we give GPT-3 this prompt, it instead actually gives very good advice. So it says, make yourself look big. If the bear approaches, keep a respectful distance. Do not run. Stand your ground even if the bear attacks. You may have to fight him off with rocks or branches. And this is actually very close to the official advice that you would get in an actual wilderness survival guide. And so this is advice that you should actually follow if you're attacked by a bear. And so what's going on? Well, what's happening is that in this previous example, if you think about it, this actually sounds like a joke. This prompt, it sounds like the setup to some joke where someone is just being comedic. And so the model is also going to answer in a joking way, and that joking way is not going to be accurate. And that's just because of how the model is trained. If you see some question that has a style that makes it seem like a joke, then the statistically most likely continuation is also going to be a joke. And so it's going to give the wrong answer. And so the general problem here is that models tend to imitate their context. So if the context appears humorous or untruthful or has some other problem with it, then the answers that the model gives will also be wrong. I want to illustrate this with a kind of more concrete quantitative example. So this is another type of prompt that you can give to GPT-3. This is a few-shot prompting question. So it says, consider the categories plant or vegetable, sport, and animal. Classify each object in its category. And then we do few-shot prompting where we give GPT-3 several examples. So it sees that volleyball is a sport, cycling is a sport, onions are a plant, billiards are a sport, pandas are an animal, and so on and so forth. And then if we ask it to predict what a lion should be, it correctly says animal. But now what happens if our few-shot prompt actually has the wrong answers, where we say volleyball is a plant, cycling is a plant, onions are an animal, so we've permuted the labels to be the wrong labels? Well, then it actually now says that a lion should be a sport, because it saw that elephant is a sport and porcupine is a sport. And so even though it knows that a lion is an animal, it will say the wrong answer because it's seen the wrong answer in previous questions. And you can actually quantify this. So if we consider this few-shot setting and look at how GPT-2 behaves as a function of the number of examples in context, then with more of these incorrect examples in context, it tends to follow the context here rather than following the original meaning. And so this is showing that if a model sees wrong answers, it will tend to imitate those wrong answers. Now, this example is fairly simplistic and probably would not happen in the real world, but there are many real world examples where this would be a problem. So one problem is that if a user writes bugs, a code assistant might then write more bugs in the same program, because conditional on seeing bugs in the context, the most likely continuation will be to have buggy code, even though what you really want is for the coding assistant to give you correct code. And similarly, for natural language models, you will tend to repeat human biases and misconceptions, even if the model actually knows what the right answer is. And so this is an example of what we'll call a misalignment, or an incorrect reward function, where what you really want is to reward models for saying helpful or true things, but it was trained to say likely things, and so you get bad behavior. So here's how we're going to try to solve this. Our solution is something called eliciting latent knowledge. So the issue is that, as we've seen, the outputs of a model might not track the truth. And so what we're going to hope is that even though the outputs don't track the truth, the latent representations of the model have information that will let us track truth information. So our solution is going to be to look at those latent representations and try to extract knowledge from them that allows us to get truthful information even in contexts where the most likely answer would not be true. And to do this, we're going to treat this as an unsupervised learning problem, and we're going to use unlabeled data to find a latent direction that tracks truth more reliably. So the picture you should have in your head is I have some input sentence, and so this is my input. And this input sentence, I have a bunch of latent representations, and then I have the actual outputs, my output tokens. Right, so this output token here is going to not capture truth. It's going to capture whatever is likely. And so we're hoping that instead, there's some latent representation that we can find that is going to be what's actually true. And so this is going to be our goal. So here's the idea that's going to let us do this. It's an algorithm that we designed called contrast consistent search. The basic idea is that we want to find some latent direction in the model that tracks truthfulness. And to do this, we're going to train a linear probe. So we're going to train a model that outputs some probability P of X. P of X is going to track the probability that a sentence is true. And it's going to be a linear function of the latent activations of the model. So we're going to take the activations, which we'll call H of X. We'll take some linear function of them, and then we'll pass it through a sigmoid to get a probability. And so we want to somehow train a linear probe where that linear probe is going to track truthfulness. Now, the problem is we don't necessarily know how to get truthfulness because the outputs of the model are not truthful. So we want to somehow get truthfulness without relying on the model outputs, and ideally without needing to add any additional labels or annotations, and only using unlabeled data. The way we're going to do this is we're going to exploit the fact that P of X should satisfy consistency conditions, because if P of X is tracking whether something is true, then we know many things about it. For one, we know that a statement and its negation should have opposite values. The probability assigned to a statement and the probability assigned to its negation need to add up to 1. Moreover, hopefully probabilities should be informative. So they shouldn't all be equal to 1/2. If I take a statement and its negation, at least one of them is false, and so at least one of the probabilities should be close to 0. So we're basically hoping that P of X will be 1 for true statements and 0 for false statements. And we're going to train a model to try to satisfy these properties. And so at a high level, the way this works is we'll take some corpus of unlabeled data, we'll create a bunch of what we'll call contrast pairs, which are statements and their negations, and we'll try to train a model that satisfies these consistency constraints. And so I'll go into more detail on how to do this on the next slide. So specifically, here's how we're going to construct our data to train this linear probe. So we're going to take some unlabeled data set of prompts, and given each prompt, we're going to create a contrast pair by filling in the prompt with opposite answers. So here's an example contrast pair. The input sentence is "I loved this movie," and the prompt is a sentiment analysis prompt. So the prompt asks, is the sentiment of this example positive or negative? And to create the contrast pair, we just fill in the answer with either positive or negative, and we can be guaranteed that exactly one of these statements is true and one of these statements is false. So these sentences are negations of each other. Then what we'll do is we'll take our model that we're trying to train, this linear probe, and we'll have two loss terms. So the first is a consistency loss, which is asking that the probability that we assign to x plus being true and the probability that we assign to x minus being true should add up to 1. The second is an informative loss, an informativeness loss, which asks that these probabilities have at least one be close to 0. So this term is asking that at least one of p of x plus and p of x minus be close to 0, because we want the probabilities to actually be 0 and 1 and not just all be close to 1/2. So what we do is we collect an unsupervised corpus of sentences and prompts. We generate x plus and x minus, and then we fit theta according to these loss terms. And this gives us a latent direction, which we, and in particular a classifier, which we hope will be more truthful than the logits. And so to test this, we can use the learned model p theta of x to classify new statements. So in particular, if we have a classification task, we can predict the positive class if p of x plus is greater than p of x minus, and the negative class otherwise. And this gives us this overall method that we call contrast consistent search. We call it that because it's trying to find probabilities that are consistent across these contrast pairs of statements and their negations. Just to give an example of how this works, if we run this method on a natural language data set and look at the resulting probabilities from the linear probe, even though this probe is not trained with any labels, it doesn't know which statements are true and false. It's only trained on unlabeled data. It does a good job of clustering sentences into the true sentences and the false sentences. So if we look at the difference in probability assigned to the positive example being true and the negative example being true, we see that these differences cluster near 1 and -1. And in particular, in the cases where the positive example is actually true, that's shown in orange here, they cluster towards 1. And in the cases where the negative example is true, they cluster towards -1. So this method actually correctly is able to classify examples. Now the question is, okay, it's able to do this clustering, but is it actually better than the model outputs? Because what we really wanted was something that is actually better than the model outputs, which might have these problems that we saw earlier. So to test this, we considered a large number of data sets, including IMDb, AG News, QNLI, StoryClose, BoolQ, Pika, and several others. And we applied our method on 6 different models and averaged over several prompts for each data set to compute the accuracy of this method. And we can see that it actually performs quite well. So our method is this method CCS that I'm showing here. And we compared it to 2 baselines. The first is just regular zero-shot question answering. And the second is something called calibrated zero-shot, which is a way of improving zero-shot answers. We also considered logistic regression, which we think of as a ceiling. Because logistic regression uses additional labeled data, it is not actually something that we are trying to beat, but it gives an idea of the best possible performance that you could attain. And so in this case, CCS often does quite well. You can see here that on average, it's about 4 points better than calibrated zero-shot. And it also, this number in parentheses is the standard deviation of accuracy across different prompts. And so you can see that it also has lower variability across prompts, and so is less sensitive to prompts, which gives some evidence that it does less context following. In addition, I guess in the interest of time, I won't go into the full detail of these results, but we show that this method does a good job of transferring across tasks. So if I use one task to fit the linear probe and then I apply it to other tasks, then I actually usually do very well. Finally, to test whether this model can actually do well, even in cases where its context would lead it to perform poorly, we test whether the method can withstand misleading prompts. So we design prompts, which we call lie prefixes, that bias the model towards falsehoods. So we do this by constructing several questions and adding answers that are either incorrect or nonsense. Here, an example would be saying, what is human life expectancy in the United States? Where the answer given in the context is 10 years, which is incorrect. And then also having other questions like, what is the square root of banana, which doesn't make any sense, and then answering with 42. And so we take this prompt and we put it before whatever question we ask the model. And in this case, the zero-shot accuracy of the model decreases significantly by a few percentage points on average, because it is misled by this prompt. But CCS, our method, can actually withstand this and continues to give truthful answers even when presented with these prompts. These are the results here. I won't go into the details, but you can kind of see here the difference where zero-shot accuracy drops when we add these misleading prompts, but the accuracy of this unsupervised method does not. And so what is kind of the upshot here? Well, the kind of takeaway here is that language model outputs are not always truthful, and this is a problem that we should address and fix. Because if we don't, then we might be deceived by language models, and this might become even more of a problem as models become more capable. And so as one way to address this, we showed that we can find latent directions that are more accurate than the outputs, and that seem to overall be more truthful. So as future work, one question is to better understand when language models tend not to be truthful, and another is to find whether we can reliably find truth in the latent representations of models. Cynthia, how much time do I have left?
Maybe 3 to 5 minutes.
3 to 5 minutes. Okay.
Yeah.
So I have a little bit of time left. So I want to briefly talk about forecasting, which is another direction that our group works on. So forecasting, how is it related to this question of making models safe or aligned with human interests? Well, the basic issue is that quantitative changes in parameter count can often lead to qualitative changes in behavior in machine learning models. This also actually happens throughout many other sciences, such as biology and physics, but it happens in particular for machine learning models. And the most famous example is in-context learning, or the emergence of in-context learning, where just by increasing the parameter count, models like GPT-2 and GPT-3 went from being able to not perform machine translation at all to suddenly being better than the fine-tuned state of the art. And there's other examples of emergent behavior as well. In the interest of time, I won't go over all of them, but it's often the case that models just obtain new capabilities simply by becoming larger. And from a safety perspective, this is worrying because, from a safety perspective, this is worrying because as we saw in the first part of the talk with reward hacking, models often also suddenly just have bad behavior as they get bigger. And so if models are gaining new capabilities and might suddenly become bad, then this is a problem, and we need ways to predict it and mitigate it. And so as one way to try to do this, we wanted to try to better predict future developments in machine learning. So to do this, we recruited competitive forecasters. These are forecasters who have a good track record on answering prediction questions, and they usually have calibrated probability estimates. And we asked them to predict progress on several key benchmarks, including a mathematics benchmark, a multiple choice question answering benchmark, and several others. And we asked them to predict performance starting from 2021 up through 2022, 2023, 2024, and 2025. And what's interesting is that relative to machine learning researchers, these forecasters actually predicted faster progress in machine learning. And so we asked them for these predictions in 2021, so we can actually see how well they did. And these are the results. So I guess I'll kind of end on this slide because I think I'm out of time. But what the results were is actually that for many benchmarks, progress was actually much faster than the forecasters predicted. So the forecasters were better than machine learning researchers in that they correctly predicted that progress would be fast, but they underpredicted how fast it would be. And in fact, the only benchmark where they overpredicted progress was robustness. So what we actually see is that capabilities of models often progress faster than expected, but their safety properties progress slower than expected. And so I think this is a big problem and motivates more work on making models safe. And so I will end there and take questions.
Thank you so much for sharing this. Would you mind? Oh, no worries. So we've collected some questions from the audience, and we'll have around 20 minutes for Q&A. So the first question is regarding the emergent capabilities in large language models. Mm-hmm. So someone commented that you've talked about how machine learning systems can exhibit unpredictable and emergent capabilities. And apart from the GPT models, are there any other examples you would like to expand on? And why do you think these emergent capabilities arise, and what can we do to prevent those?
Yeah, that's a great question. So I'll go back to this slide where I gave a few other examples. So one other example of emergent capabilities is a phenomenon called grokking, where models actually, as a function of the number of training steps, often can go from not generalizing at all to generalizing nearly perfectly within a relatively small regime. So right now, this happens most commonly on symbolic tasks like modular arithmetic or other simple mathematical tasks. But it's somewhat worrying because it suggests that even the same model, if you just train it for more steps, might suddenly become able to do something that it was not able to do before. And we see evidence of this in some other cases. So for AlphaZero, which was trained to play chess and other games, there's a phase transition where around 32,000 training steps, it suddenly acquires many human chess-related concepts that it did not have prior to that. And one other example is that some models seem to have gained an emergent ability to utilize side information where retrieval-based methods just go from not working very well to working much better, just as a function of number of parameters. Maybe another example would be chain of thought reasoning for models such as Palm and Minerva. To answer the second part of your question of how we can prevent it, I think it's probably not possible to prevent all forms of emergence. And in fact, some forms of emergence are actually good. In-context learning is certainly a good behavior. What we want is to avoid bad emergent behaviors. And so I think the sorts of bad emergent behaviors that we want to prevent would be things like deception or goal-directedness or other things where models might act against human wishes or human goals. And so for that, I've been trying to understand how goal-directedness emerges in other systems like humans or other animals as a consequence of evolution. I think if we could understand that better, then we might be able to prevent it in machine learning systems. Also, another approach is to try to understand the latent representations of models better via better interpretability techniques so that we can detect goal-directedness or other bad behaviors and get rid of them.
Yeah, thanks for answering this. And we received our second question about truthfulness of foundation models. So someone commented, you talked about eliciting latent knowledge as one of the lenses for addressing the truthfulness of language models. What's your vision for the future work to address the truthfulness of foundation models, such as large multimodal models?
Yeah, that's a great question. So these experiments were already on foundation models such as GPT-2 or other large pre-trained models, but they were only trained on one modality. I think if you have multiple modalities, then that could potentially help you because you have more consistency constraints to work with. If there's a statement that can correspond to something in some other modality, then keeping track of consistency across modalities might help you better pinpoint truth. And so I think that could be an interesting direction.
Yeah, thanks. And this third question, we know that it is still difficult to make a substantial breakthrough in the trustworthiness of NLP large models. And do you think there are any practical tips that can play a temporary role in engineering applications? For example, are there any engineering techniques that can be used to guarantee credible output of large language models?
So for engineering techniques today, I think one thing that seems very important is just the type of data that the model is trained on. If you train on data that has toxic speech or that has inaccurate statements, these models will tend to remember at least some of that and so reproduce it once you use them or when you fine-tune them. And clearing that out of the training set and keeping only high quality information seems to help a lot. So I think that could be one possibility. Another would be if you can fine-tune models, perhaps based on human feedback, to be more trustworthy. The only problem with that is that then you can only be as trustworthy as humans are able to detect. And if there's questions that humans would judge incorrectly, then the model will tend to judge those incorrectly as well. But for short-term engineering challenges, this might still be good enough.
Sure, thanks for sharing. And our next question is about speed of progress. So you talked about how ML capabilities are progressing faster than expected, but safety is progressing slower than expected by professional forecasters. So what do you think are the main reasons, and are there any structural changes that you think need to happen in the machine learning field to address this?
Yeah, that's a great question. I think there's a few. One is just that it is often easier to advance capabilities than to advance safety, because safety often has to do with robustness or other types of out of distribution behavior, whereas machine learning models are very good at doing well on distribution. And while foundation models often are much more robust than smaller models, they can still have problems. That's one issue. The other is that for issues such as reward hacking, large models might actually be even worse. And so since there's a trend towards making models larger and more capable and more powerful, that could actually exacerbate reward hacking. In terms of what needs to be done to fix it, I think part of it just begins with the research community putting more attention onto it. There's probably many more researchers that are trying to advance capabilities than that are trying to make models safe. And so the more people doing that, I think the better situation we'll be in.
I see. So a little bit follow up on that. Do you think you still recommend that people maybe can read the unsolved problems in ML safety?
Yeah, I think we lay out a number of concrete research directions that could be followed in unsolved problems in ML safety that I would definitely recommend people look at and try to work on.
I see. So maybe someone from our group can post the link to this paper in the chat. Okay, so the next question. What are some advantages and disadvantages of other paradigms that avoid designing reward functions? For example, learning from human behaviors, example-based reinforcement learning, or inverse reinforcement learning?
Yeah, so I think learning from human behaviors or inverse reinforcement learning have still a problem, which is that the model ultimately is just being trained to predict the human behavior. And we're then hoping that there's some latent concept in the model that we can access that corresponds to the actual goals that the humans have. And then that gets hooked up to the model. But I think it's not guaranteed. And so we either need more robust ways of making sure that the goals that are inferred by those methods actually correspond to human goals, or to combine that with interpretability techniques, such as some of the ones that we described in this talk, in order to actually find latent goals, even if they're not easily identifiable.
I see. Yeah. So the next question is, are there risks with large pre-trained models that are impossible to solve? And what are the causes of these risks?
That's a great question. I guess I have learned through my practice in forecasting that it is always dangerous to assign probabilities that are 0 or 1. So I'm hesitant to say that that anything is impossible. I think one of the biggest risks that I'm worried about is deception, where if we train models to get high reward according to human approval, the models might be incentivized to do things that look good to humans, but are not necessarily actually good. And so this could lead to deceptive behavior and in fact incentivize models to be very effective at deception. And I don't think this is impossible to solve, but it seems very challenging, and I think is something that that we should be trying much harder to prevent.
Yeah. So among these possible choices of like safety techniques, Which one do you think might make AI systems as safe as possible and also as soon as possible?
So I think that there are, I guess we're so early in this field that there's different paradigms, and I think we don't know for sure which paradigm will work. I can outline a few that seem promising to me. So I think one is if you can get models to be truthful, then even if models are, for instance, know things that humans don't, we can still extract that knowledge and kind of use that to guide decision making. So I think that's one approach. Another is if we can get very good at interpretability and understand a lot about what is happening inside of models, then we could use this to detect deceptive behavior or other bad behaviors in terms of the model's intent. And then I think a final approach is if we actually just avoid ever training models that are too large and only start with models that are, let's say, only 100 billion parameters. So still quite large, but just not as large as, say, a human brain. And then we can kind of combine these together in ways that are well understood. I think that is potentially also a way to avoid at least some safety problems. But I think for all of these, there are many open questions, and it is not clear if any of these will work. I view these more as directions that we should explore to understand their limitations and strengths.
I see. And speaking of interpretability and also reward hacking, someone asked, what do you think about the relationship between causal inference and AI safety?
So I would say that in some sense, the contrast consistent search idea that I showed has a bit of inspiration from causal inference, because you can think of this method as actually creating a kind of intervention, right? So when we go from x plus to x minus, what we're doing is we're finding a way to change the truth value of a sentence while keeping all other properties of the sentence unchanged. And so it's almost like a do operation in causality. And I think having these sorts of counterfactual interventions is very useful for being able to identify pieces of models that do different things, right? This was very useful for helping us to find the piece of the model that tracks truthfulness. And so I think that is one potentially promising connection between causal inference and safety.
Do you think it's a promising approach, or is people being too hyped on causality nowadays?
Well, I would say there is a lot of hype around causality. So I don't know so probably there's too much hype. I would say the thing that seems most promising to me is connecting causality to interpretability. And in particular, probably not thinking so much about classical concepts like propensity weighting or things like that, but more thinking about, can we use counterfactual generations as a way to find interesting facts about latent representations as a kind of experimental paradigm.
I see. So the next question is something relevant to beyond the imitation game. So someone commented that it seems that many of the current large language models are trained to predict the next tokens or imitate human behaviors without explicitly optimizing for truthfulness and fairness. And eliciting latent knowledge seems to be a method to detect these failure modes. What are your thoughts on how to steer the models to unharmful behaviors beyond detection? And do we address these problems from incremental interventions on the dataset selection or training procedures, or do we need a qualitatively different approach?
Yeah, that's a great question. So I would say that eliciting latent knowledge doesn't just help you detect it, but in some ways can help you get around it. If you replace the regular output head of your model with the with the linear probe that you get from eliciting the latent representations. So you can partly mitigate it that way. You might not be fully happy with that because there's still lots of pieces inside your model that are computing things you don't like. They might be computing things that have to do with bias or deception or other untruthful concepts. So I think we don't currently have great ways of getting around that. I think probably you would want to do, probably some form of adversarial training to try to train out the bad concepts. But I would say that this is more of an open research direction that we need to understand better rather than something that we can easily do today.
Yeah.
But it's a great question. Yeah, I definitely, it's thinking along the right lines.
Yeah. And so our next question is, do you think there are any boundaries beyond which we should not deploy machine learning systems?
I think it's possible that we should avoid training models that are too large until we understand the consequences of doing so. I don't know exactly how large is too large, but I think given that emergent behavior can often be surprising, as models are becoming so capable that they can, perform complex reasoning, maybe they'll start to be able to make complex plans soon, then the cost of deceptive behavior or other misaligned behaviors could be very high. And so we should have a very high bar of understanding what the models are doing before we deploy them. And I think currently we understand very little about what the models are doing.
I see. And currently, I think the engineering, like the most companies are deploying more of languages and computer vision techniques in the real life application. And do you think it is part of the reason why RL applications are not that widely used at the moment?
I think it's more that reinforcement learning doesn't work very well right now. I certainly am more worried about reinforcement learning because it seems much more easy to get goal-directed behavior. But people are already starting to hook up language models in ways that involve goals or volition. For instance, hooking up language models to interact with web pages or other external tools. And so I think even with just language models, you could end up with dangerous behaviors, and that we should probably think more carefully about what we're doing there.
I see. Thanks for sharing this. And maybe we have our final question. Do you have any closing remarks or advice for our audience who are mainly graduate students in AI?
I would say, the most important thing is just do great research. I think if you do good research, everything else follows from that. When I was a graduate student, I used to stress out a lot about other things. It's like how many people retweet your paper tweets and this sort of thing. And at the end of the day, I think good work gets seen, even if it doesn't get retweeted on Twitter. People will read it and remember it and build on it. So that would be my number one piece of advice: is just good research is the most important thing.